All right, thank you. First, I would like to acknowledge all the people who have contributed to this work. It's a long list, but I would like to particularly point out to Carlisle Thacker, who passed away about a year ago. He was really helpful in doing this work. And the way I came to know Carlisle, actually, is kind of funny. I was still a graduate student in the mid-'80s. I would go to the stacks in the library. This is before PDFs were available. And I would look up an article in the Journal of Fluid Mechanics. And then there were so many interesting articles, I forgot about the reason I was there. And I encountered one of his early papers where he solved the shallow water equations with a moving boundary problem. So that was really hard. It was an analytical solution. And everybody who does storm surge calibrates their model with his solutions. It only works where you have a parabolic bathymetry, but I thought it was great work. Years later, I encountered him. So this was only a small part of what he had done. He was well known for sort of advocating adjoint usage for data assimilation. He worked on solving the shallow water equation on the sphere. He was really prolific and very open about his work. And his contribution to this work was mostly to bridge the gap between people who sort of were enamored of polynomial chaos methods and spectral expansion, and the people who came at it from a statistical point of view. And so if you build a surrogate model using polynomial chaos or use Gaussian process, dependent on your background, if you came from the world of PDEs, you went to spectral expansions. If you came to the world of statistics, you came to Gaussian process, and sort of Carlisle made us kind of bridge the gaps between the two, actually. So I'm going to talk about a work that we've done in this sense. So these techniques are really useful if you're trying to explore a small parameter space. And the main attraction from my point of view is that the ensemble you need to build these surrogates or emulators is relatively small compared to what you need for a deep neural network. So I would like to focus on a couple of applications, give an overview of what these things are about, give an overview of their limitation, and then spend most of the time on the application. And this is going to be about the ocean. So the atmosphere is present, but in an indirect way. So this is my slide about what we mean with UQ. We have a dynamical model here that takes some certain inputs that are uncertain. It makes the output M uncertain as well. And this is shown in the blue PDF of it. And so the main goal is to sort of propagate the input uncertainty into output uncertainty. And if we do actually have observations, and this is the magenta PDF that is shown on the output, well, maybe you can do some Bayesian inference and learn about your input uncertainty and do some back propagation. And the example I'm going to show essentially does this complete circle where you do have observation and you can sort of compute their impact on the models. And so typically your uncertainty space is very large. And so what you would like to do is to run your dynamical model to actually get a few samples, shown here on the left, and then from this small sample build a surrogate that you can use for the statistical analysis. And people have done this in one of two ways: polynomial chaos expansions and Gaussian process. And nowadays you can do it with deep neural network as well. So this is my one slide about like the different strength and advantages of each of the different techniques. Deep neural networks try to sort of cover all possible flow regimes, all types of situations. And so the data set needed to train them are actually quite large. So the focus here is on the other two approaches to do these UQ studies, polynomial chaos, which, you know, if you look at it from afar, is nothing but separation of variables and casting it into a series, and Gaussian process regressions. And both have the advantages that you can build a surrogate with a relatively small ensembles. Usually the more ensemble members you have, it's the better. But you know, you're really limited by the amount of members that you can afford at any one time and the time it takes to produce them. And this is why having forward model and dynamical models that are GPU based are extremely useful. So a few words about emulator or surrogate models with polynomial chaos. It's really nothing but capturing the dependence of your output M on the uncertain variable xi. So you want to take that into account. And the way you cast it is essentially as a series with basis function psi sub k with unknown coefficients, and you truncate the series somewhere. So the behavior of M with respect to the uncertain parameter is captured through this basis function, okay? And the basic questions are, you know, how do you choose the basis function? How do you determine the coefficient M sub k, the hatted ones? And where do you truncate the series? And you get different flavors of polynomial chaos depending on the choices you make. So first, why a series? Well, it's because it's very convenient to analyze. It's easy to handle. So if you want just to produce surrogates of the model, it's very efficient to calculate it. You can sum it millions of times and build your histograms this way. If you can integrate your basis functions because you chose them, and so you know how to do these integrals, and so you can compute statistical moment, for example, in your parameter space and do the variance. Moreover, you can differentiate the series and get a pseudo adjoint for your model, at least with respect to these limited parameters. So it's really nice to actually have a series that you can manipulate easily. How do you choose the polynomials? A really convenient choice is to use a basis functions that is orthonormal with respect to the input PDF. So if you know how to characterize the PDF or your input uncertainties, choosing a basis function that is orthogonal with respect to that basis is useful. So essentially, the formula that you see on top defines an inner product, and it makes the basis orthogonal. And you can always make it orthonormal. And so this is just a spectral representation of the dependence. And the series converges very fast for smooth functions, which is very helpful. So the common choices for basis functions depend on your input distribution. So if you have a Gaussian distribution, these would be Hermite polynomials. If you are in a uniform, these are Legendre polynomials, Jacobi polynomial if you have beta, etc. So it's extremely convenient. And if, yeah?
Does your sampling have to be from your prior?
It has to be what?
From your prior?
There is no prior yet. I will mention, okay. Yeah?
What dictates the choice of row here?
Well, it's actually your data. Is your data Gaussian? Are you presuming that your uncertainty is uniform in the input parameters? It's really up to you to decide. If you use uniform, you're saying, I don't know much about the distribution of my input data, and I will choose the uninformed one. And dealing with Legendre polynomial is the easiest thing. If you know it's Gaussian, then you go towards Gaussian distributions. Yeah?
For empirical distribution, are there non-super expensive way of building the basis or the size?
I think you can, if you have an empirical distribution, you can probably build a set of orthogonal polynomials that satisfies these relationships.
There's no like cheap go-to way of doing it because it may be very expensive, right?
I don't know, I never tried it. But I think there are ways of doing it. And I think there's a way of sort of building adaptive bases. And those are based on constructing the orthonormal basis. Yeah?
Is it important that they are polynomials? Or they could be generic, like basis functions? Because if it's generic basis function, there are methods to define for, like kernel methods, for instance.
We've only tried it with polynomials, and there's a real nice benefit if you use polynomials, and they're orthogonal, because then the statistical moment becomes really easy. The mean is just the 0th order coefficient, and the variance in your output is the sum of the square of the other coefficients. So, and this essentially gives you a way to monitor how good your series is. If you still have a lot of power in the high order coefficients, you're missing variance, you need to make it longer, etc. Okay? So it gives you a way of monitoring whether your series is accurate enough or contain enough of the variance contributors. How do we determine the PC coefficients? Lots of choices there. And so what you want to do is to minimize the approximation error between the output M and your series representation of it. The straightforward one is the Galerkin projections, and you minimize this type of norm, the L2 norm. And so that amounts to computing this integrals, which you can do with Gaussian quadrature. And this is this formula here. So the real cost in here is to compute this term, M sub psi. And so you can perform these calculations with an ensemble. You just have to run the models at specific values of the uncertain input. You collect enough of them at the quadrature point, and you can compute this integral. So it makes it as a post-processing step, okay? And that's one way of doing it. And you can do, so essentially you're doing quadrature in multiple dimensions that has its own problems and the curse of dimensionality that comes along with it. But you're not sort of limited to that. You can choose to do a least square minimization of the problem. That works as well. You just have to make sure that your design matrix is invertible. And there are other ways to do it. You can decide that you want to build a sparse basis from the get-go and just keep the terms that contribute the most accuracy to your series. Yeah?
So in the first method, you have to run the model S times again as a post-processing step?
Yeah. So it will cost you in storage and CPU time.
I think maybe I just got lost in the notation of it. Where does the model M of x come at the end here?
So you're trying to evaluate this. You replace this, you approximate it with a quadrature. And the quadrature requires that M be available. And this is actually your model run. because remember, you chose the basis function, so you know what that is. You have the quadrature weight, and so you're missing this piece.
But wasn't there an x comma t as well?
I suppressed them because it doesn't fit on the slide, but this is space and time dependent. You can do it at every space-time location in your model.
So the m hat case depends on space.
Yeah. So the basis pursuit denoising is really nice because it sort of keeps only the terms in the series that are needed to decrease your error, and it can handle all sorts of response functions. And the best approach of these things is to be able to do adaptive sampling. So you do a first batch of samples, you build a first series, and then you test whether you have enough accuracy, and then you go and do additional experiments. Never starting from scratch, always reusing the previous work that you have done. So you're sampling the most important regions of your uncertainty space that contribute the most to output variance. And you can do these things with any of the other techniques, Galerkin or basis pursuit denoising. We started by sort of playing with Galerkin projections. Their main drawback is that the quadrature rules are kind of rigid. If the model fails because it's outside its operational range, you can't use the technique. You have to do something else. The other portion is that the quadrature sample cluster near the edge of the space instead of near the center of your distributions. And so model failure at a single point can ruin the entire calculations. Least square is really useful when your response surface includes noise and your samples need not be constrained by quadrature. You have to invert a matrix. The compressed sensing is really useful as well in those techniques. And it's really advantageous if you can couple it with adaptive sampling. So it's really useful. We found it to be extremely helpful, and at least if you come from a background of solving differential equations, the setting makes a lot of sense. You're just doing it in parameter space rather than in physical space. The really hard part is that it cannot handle very large dimensions of your parameter space. If you have to perturb a field to get the uncertainty, you have to be able to boil it down to, I don't know, I would say 6 or 7 parameters that you can pursue. Other groups have gone up to 20 parameters. We haven't been that adventurous yet.
Can I ask?
So, yeah.
So the reason that this is challenging to scale to large dimensions, or at least is it part of the reason that the polynomial basis is basically like a tensor product basis,
yes.
that you need as many, somehow exponentially many
Correct.
elements as the dimension?
Correct.
So then maybe it is worthwhile considering some type of non-separable basis in the input coordinate, like from a kernel eigenbasis adapted to your row distribution.
Yes, it could be useful. The sampling strategies, the adaptive sampling strategy, and the Smolyak type sparse quadrature tend to sort of drop off elements that are in sort of the cross dimensions. So it focuses on unidimensional exploration as opposed to cross terms. in the series. So, but yeah, I don't know about sort of, I mean, in a way, GP is a kernel methods. And when we compared the two approaches on the same problem, they gave about the same type of accuracy, actually. So we applied this to actually a lot of problems, pursuing quantifying uncertainties in forecast, mostly in the ocean and somewhat in the atmosphere. The most fun one was to actually apply it to a biophysical model of larval connectivity in the Caribbean. But what I would like to talk about is essentially the Bayesian inference of drag parameters using AXBT data from Typhoon Fanapi, because it does close the loop on propagating the uncertainties forward and then backward to learn about what you're doing. Okay? And so the idea behind this was when there was a large campaign to sort of monitor the ocean conditions in the Pacific. And during Typhoon Fanapi, they just dropped a lot of AXBT data to actually measure the condition of the oceans before and after the passage of the storm. And so we thought we could use this data, mostly temperature data, to learn about the drag coefficient at high wind speed that is in HICOM. And so some of the questions are, what's the saturation drag coefficient? What's the wind speed at which saturation is reached? And does the drag coefficient decrease for wind speed that are larger than the maximum? And so this is kind of my slide to sort of summarize all this knowledge. The formulas on the right is our forward models parameterization of the wind stress on the surface of the ocean as a function of the 10-meter wind speed. And so we're going after this parameter, C sub D. And this is the parameterizations. It's a polynomial that depends on the difference between sea surface temperature and air temperature. And what you see in the figure are what was known about this parameterization for a while. So let me actually try to walk you through this. The thin red lines are essentially laboratory experiments of the parameterization that were done at the University of Miami by Mark Donnellan. And you see that the wind drag increases linearly until it kind of saturates at some point. The green data, the green line, are drop sounds from Power et al. And they suggest that sort of the wind drag coefficient decreases at some point and drops. The blue dots actually are aircraft measurements that were also done at AOML, I think. And I just admired the bravery of the authors. They actually sort of they provided their data. It's a little bit all over the place. But the idea here is that, the drag coefficient saturate. We're not sure what this saturation level is. And then sort of at which speed it saturates. And so we decided and whether there was actually indeed a decrease in the drag coefficient after Vmax. So we decided to perturb these with three parameters. Alpha, which is just a multiplication factor, to perturb the reference speed, and and Vmax. So we varied it between 20 and 35 meters per second. The reference was about 32. and m, which was 0, that's the slope after the maximum. And the idea is to use the ITOP data and Bayesian inference to learn about the likely distribution of these perturbation parameters. And so to do it in a sort of Bayesian way, so we want to be able to build the posterior of all these things. And so this is our likelihood function for the observations. The T sub i's are the individual measurements. The M sub i's are the model estimates of the measurements. And this is where the surrogates will come in. And the other parameters are the priors on the uncertainty of the observations, the multiplicative factors that tell us where the drag saturates, Vmax, and the slope. And so we're going to rely on the series, the polynomial series, to replace this and be able to draw 50,000 sample of MI. And so these were the flights that were performed ahead of the storm. So Fanapi started as a tropical storm on September 14th, and then it intensified to a category 3 on September 18, and it made landfall on September 19 in Taiwan. The yellow circles are the places where the drop sounds were released, the circles. And this box is our sort of criteria to do the adaptive sampling. It shows a box where the hurricane was close by and was very intense. So these are some slices from our adaptive sampling technique. So you do it by levels. And so you sample along the M directions and the Vmax directions. And if you see, there are lots of sample along Vmax, not a lot along M. And so you're building this kind of sequentially. You're running the ensemble by batches. We were able to build a surrogate with 67 samples. How good are the samples? Well, we actually measured the representation error, the approximation error of the series, and it looks pretty good. The measurements are in blue. The polynomial series is in red. They're very close. So the left panel is the sort of the comparison of the two directly, and the right panel is a normalized error that stays below 0.1% for most of the simulations. This was in the box. That was the spatial average of the sea surface temperature. But you can build the representation error at every spatial point you have at any depth you want. So these are contour maps of the normalized error. They're very small. The top row is for the surface, and the bottom row is the top row is for 9:15 before the passage of the hurricane, and the one on the 18th is when Fanapi became a Cat 3 hurricane. Most of the errors are at the base of the mixed layer, about 50-meter depth, but the errors are still acceptable. So again, this gives you the ability to sort of compute the statistics of your ensemble. And so what you see on the left are the mean temperature, and on the right are the standard deviations. So the different simulations differ by what's happening on this side. So you have about a 2-degree cooling after the passage of Fanapi from 30 Celsius to 28, and the uncertainty confined at the top 50 meters. And you can make slices through your parameter space, see how the SST response surface at a particular place depends on the uncertain parameters. And you can tell immediately that it depends strongly on this multiplicative factors. The gradients are very big, and not that much on Vmax. And it changes as the time evolves. So we went ahead and did the Bayesian inference. The red lines are the priors. We used uniform priors for this work. And the blue lines are the posterior. It's nice to have a full posterior of these things. And we were able to the posterior of Vmax seem to be pretty peaked at about 34 meters per second, slightly higher than the unperturbed value. The alpha parameter was slightly larger than 1, so it's a higher saturation for your drag coefficients. And as far as the slope after saturations, the posterior and the prior look very similar. So essentially, our data isn't telling us much about the behavior of the drag coefficients afterwards. And the sigma is essentially telling you how well our observations our model results fit the observations. And it increases slowly as time evolves. So this was nice. And we did this again with an adjoint type calculations, and we pretty much got the same results. So I already said these things, so I don't need to dwell on them more. And then so you can build the joint posterior of the PDF and see how much it's pretty sharp in this case. And this is essentially the drag coefficients that fits the data best. So you're able to compute that as well. This is another one, so let me skip it. Moving on to applying Gaussian process regressions. It's an interesting debate. So it's just an overview. It's a completely different approach to perform the analysis. Instead of a polynomial series, you're saying that M follows a Gaussian process with a specified mean and a covariance function. And what you have to do is specify these two things. The most important part is specifying the covariance functions. And so this is all the math that you need when you're in the continuum. But when it comes to discrete data, your Gaussian process becomes a multivariate normal distributions. Your background functions becomes a vector of prior means. And your covariance function becomes a covariance matrix. And so this is the critical tool that we have. And so what you have are the data collected, M sub D, and your covariance between the data. And what you would like to do is reconstruct the field at unseen locations, shown here as M super T. And so if you condition, everything is supposed to be normally distributed. So if you conditions on the data, you get your analysis update, you get a posterior mean, and you get a posterior covariance. These are the formulas for these things. They're very similar to what you get with, they are the mathematics of optimal interpolation. One big thing about Gaussian processes, you get the posterior mean. That's your best estimate for what for your quantity of interest, but you also get an estimate of its variance. So that's kind of nice. So at the time, University of Miami was engaged with sort of deploying massive amount of drifters in a concentrated area to try to study sub-mesoscale field. And we thought we could use this approach not to sort of look at UQ of simulated data, but at real observations. And the idea behind it is to try to reconstruct the velocity field to calculate frontal divergence, vorticity, and strain. So let me sort of give you an example of what that is. So the drifters were dropped into this little white box here, black box here. These two pictures show sea surface temperature from satellite and chlorophyll concentrations. And you see a little sort of sub-mesoscale feature here in the sea surface temperature. And you see a front. There was a survey that was done that collected information. You see a front. And all these yellow stars are essentially the 326 drifters that were deployed in 14 hours. And so by collecting the position of the drifter as they were being moved around by the current, you can get an estimate of the current. And these are point-wise estimates. What we would like to do is cover this with a grid using GP and take derivatives of these things, finite difference derivatives, to try to fill in the gaps. And from these derivatives, compute kinematic quantities. Okay? And what is challenging is when the drifters start lining up like this, you lose a lot of spatial coverage very quickly. So it becomes very hard to compute the divergence of the currents or the vorticity of the currents. You want them to be spread on a sort of rectangular grid. Unfortunately, the currents have their own minds. So we applied the Gaussian process regression to these things. The one innovation we did was to actually specify a covariance kernel that has 2 length scale, 2 time scales. And this was our attempt at trying to sort of account for the multi-scale nature of the data. And so all these Rx's, Ry, and Rt's are hyperparameters. The covariance function is a fairly standard squared exponential with a variance and a decay length scale. The innovation here is to try to sort of put 2 space-time scale in here and try to identify the 9 hyperparameters that come up. So we have 8 from the covariance kernels, and sigma is a noise level in the data that we also are trying to infer. And so we used, we maximized the log marginal likelihood of the parameters given the data. We had about 16,000 observations, and we treated the 2 velocity components separately. Yeah?
I was wondering if you could comment for like intuition. If you were to take, say, a product of two scale Gaussian kernels, is this something that you've considered trying as opposed to a sum, and how it might similarly behave?
That was my original idea. Raphael had slightly different ideas, and he decided to sum them. You can take products or sums. And I think what the sum offers you is to get a scale for the second sort of sub-mesoscale features. That was helpful, actually. So we did that and through the data. And so these are the parameters that come out for each velocity components. So the noise level was about 1 centimeters per second. You couldn't, the data wasn't useful to get better accuracy than this. Anything with a subscript of 1 is the sort of larger length scale and time scale that we have identified. So it's about a 3-hour time scale for the U and V components, and about 3 kilometers in the X and Y direction. There was another scale occurring smaller than that. So the variance of this scale was about 13 centimeters per second. So that's the signal. The second scale had a signal of about 3 centimeters per second, and a much smaller time scale is about 40 minutes, and much smaller length scale as well, about 400 meters. So we tried including a third space-time scale, but it turned out to be below the level of the noise, and so we stopped that too. So that was kind of a nice innovation to get these two length scale. So how well is this Gaussian process? We held 50% of the data as training data and reconstructed it with the Gaussian process. And these are the histograms of the reconstruction for each of these components. This is the cumulative histogram. And so about 90% of our reconstruction has less than 2 centimeters per second error, and more than 99% had less than 4 centimeters per second error. So that was kind of nice. Even when you looked at the normalized error, things looked very acceptable. The other thing that we wondered about is, well, since the GP gives you an estimate of the posterior variance, how good is that compared to the actual error that we measured? And these are the histograms that you see below. And it looked like the GPR overestimated the error by about 1 centimeters per second. So the estimates were conservative in that sense, and that gave us additional confidence in the results. So with that, we actually reconstructed the velocity field on a 50 by 50 meter grid. Zone with posterior errors greater than 4 centimeters per second were masked, and we computed the relative vorticity, divergence, and strain of this technique. And so this is what it looks like on these regular grids. So the arrows are the actual measurements, and the colors are the speed of the reconstructed fields. So the purple arrows are the measurements. The black arrows are the reconstructions. And so you see the formation of a sort of a slow zone here that gets elongated as time goes by. The more interesting one are the measurements of the divergence. It's very hard to sort of observe ageostrophic flow. This one is scaled by the Coriolis parameters, and we were able to detect divergence that were 8 times the planetary vorticity locally. So other reconstruction techniques, you kind of smear the signals so you never get these gradients as sharply. Same thing with the relative vorticity. You could detect over the convergence zones how the relative vorticity is 13 times the planetary vorticity. So you're in a very strongly non-geostrophic regime. And you can compute the strain rate likewise. All of these things are essentially evidence of submesoscale activities and instabilities. So I'll end with a few remarks about the GPs. What you have to do with GPs is to specify the kernel functions. It requires the inversion of matrices, which makes it, which limits the data sizes. In this application, we were able to get away with specifying multiple scale in the kernel functions, and the data was able to identify multiple scales. It's also very nice that it's able to deliver estimates of the uncertainties of the output. A major drawback is the dependence on the coordinate system. And we haven't found a way to sort of overcome that. Other groups have tried, I think, with kind of mixed results. The biggest drawback is the fact that you're relying on stationary kernels. The square exponential is a stationary kernel. And that's OK if your flow has the same features everywhere. But if you're dealing with a front and you're mixing what happens on two sides of the front, a non-stationary kernels would be really nice. Except if you try to design it by hand, it will be problem specific and sort of not very satisfying. It would require case-by-case customization. Maybe deep Gaussian process is the way to go and try to address this problem. So,
Did you try this experiment without using the multiple scale kernel function and see if you had any different results?
Yeah, we did, definitely. And Raphael has a picture of the paper seeing the impact of the small scale, how they enrich the field actually quite a bit.
Great, thank you.
So, and with that, that's the end of my presentations. I really like these techniques that you're exploring sort of a small parameter space. You're looking after a process, and you're trying to quantify the impact of these parameter perturbations on the output. So, thank you.